Good morning, this is Jim Hennager. It's Monday, November 23rd, here in Nevada, Iowa, for the New Independent Party. This is our table talk. The topic for today is going to be global warming, and I think for what I would like to present today, there's a host of issues related to global warming and climate change that I don't think are coming out, and I think there's some biases related to the kinds of special interest again who would like to see this issue go in a certain way to try to influence legislation in a certain way or government spending in a certain way. So you have the different camps here, or the different special interest groups. You have those people that would like to see money made in an entrepreneurial way on sustainable energy, like wind energy and solar energy and biofuel, the ethanol plants, those kinds of subsidies, tax credits, and it's a huge business. Some of our largest energy companies didn't pay any taxes last year because they were able to get the tax credits on the windmills, for example. Some of them pay $500,000 a year in tax credits. So it's a huge business, as well as, the federal government has given millions and millions of dollars to startup companies to develop new energies. And it's an entrepreneurial kind of adventure for people to get into, and of course those people that get into it get the money. They have a tendency to give money to certain politicians, and it's that kind of cycle. On the other side, you have those people that have more traditional energy sources, such as coal. They're fighting a lot of the legislation, and they're trying to deny that there's a major issue. We also have the oil industry, who are still making a lot of money producing oil and selling oil. So they also have a vested interest in what direction government is spending its money. There's a third area, though, that has developed over the last 30 years where they would like to see something called cap and trade, where they would like it to work out that those people that are polluting the most, companies that are polluting the most, have to pay into a fund, a penalty each year, and then that fund gets divided out to reward those people who are taking care of their pollution or lessening their pollution. And this goes along country lines in many ways. Some countries are heavier polluters than others, and what they see is a giant administrative center here where the funds come in and get divided up and funds go out. Well, obviously, whoever's in control of that administrative group in the middle are going to see literally hundreds and hundreds of millions of dollars, if not billions of dollars, go through, and they're going to want an administrative fee. So you can see right away that they have a bias. They want to see this cap and trade and be right in the middle. In fact, I know of one UN person from our neighbor to the north who's actually gone and set up offices in China because he thinks, because China is one of the larger polluters, that why not be right there where the fine is going to be issued. However, they haven't moved in that direction entirely, and it's still being debated. So you have all of these groups kind of arguing back and forth, and what we've ended up with is one side basically saying we are warming up globally and it's dangerous and it's being caused by man. The pollution, the increase in carbon dioxide is creating a greenhouse effect that's causing this warming. And if we don't do something, within the next generation, the seas will come up and the weathers will change, and some parts will be very arid and desert-like, and other parts will have storms all the time. Now the other side, sometimes called the deniers, they're saying, well, it's not that serious, and it's not completely caused by man, that there's very little that we can do as humans to change the direction of a global kind of event here. So, looking at all those sides, I have to say I'm not an astronomer. I'm not a weather person. I'm not a person who has studied in detail all of the variables. But just looking at it from how I would talk about it in my classes, social problems, it is a social problem because it's coming at us very quickly. And I can just recount that when I was a boy, the average Earth temperature was about 54, 54.2. Now, when we get into how those average temperatures are figured, that becomes somewhat of the issue because we have over 2,000 weather instruments all over the globe. They're on mountaintops, they're on plains, they're on buoys out in the sea, and we're basically talking about surface temperatures taken by 2,000 instruments. They may take a temperature reading every hour, and so what you're doing is taking 2,000 instruments, a temperature reading every hour, 24 hours a day, 365 days a year. You're taking all of those measurements and then dividing it so you can come out with an average Earth temperature of the entire planet. So if 60 years ago the average Earth temperature was 54.2, today in 2014 it came out 58.2, 58.4. So in 60 years the average Earth temperature has risen 4 degrees. Well, 4 degrees doesn't sound like a lot, but it really is when you're considering that reflects, the upper temperatures, those temperatures in the 80s, 90s, and 100s actually increasing all over the world, and the bottom temperatures aren't offsetting it. So if you're looking at the Earth over a long period of time, and I'm talking about millions of years, if we went back to when we had dinosaurs here and no humans, the average temperature may have been well above 60, and the temperatures would have been 80, 90, 100, 110, for a large part of our planet. And actually, from the core samples that they've taken over the years, they've determined that the carbon dioxide level 60 million years ago was 4 times as high as it is today. So, if you're looking at this argument that it's global warming is caused by humans, and that the biggest part of that is the carbon dioxide that we're putting into the air, there's been times on planet Earth where it's been a lot higher and there were no humans around. So the first thing I'd like to emphasize is that the Earth temperature goes up and down, and it has gone up and down over centuries, over hundreds of years, thousands of years. In fact, we have evidence that there's been at least 5 major ice ages. And obviously during an ice age, the average temperature may drop below 50 degrees on an average. So if you looked at it, like a thermostat you have in your room, that thermostat probably goes from a low of 50 or 30, 40 degrees, 46, 48, 50 degrees when there's an ice age, and maybe 60 to 64 degrees at the top. But in the time when humans have been around, it's probably, in the last 10,000 years, varied between maybe 52 degrees and maybe 60 degrees at the top. So the Earth has its own thermostat, and I'll get into it in a little while, but it actually, if it gets up to the top level, there's mechanisms, there's dynamics that actually make it go in reverse. And there's probably dynamics when it's at its lower that bring it back up. So we're fortunate in that regard that we don't live on a planet where it goes 80 below zero or 800 below zero and stays there. We're on a planet that has a range, a temperature range, where astronomers, astrophysicists call us a warm planet, and not entirely stable. That's the part that we have to understand. there are vested interest in government and business and in science that would like us to think that we're living on a planet that's very stable and doesn't change. There's no dramatic geological kinds of events, but that's just not true. In fact, we're living on a very, semi-stable planet, and the reality of that has to be considered in what's happening today, because things change constantly on our planet, just as they do every place else in the universe. And we need to understand that those changes have an effect on weather, and in this case, the global warming. So let me just kind of outline some of the issues of why things change, so we can understand that this is a much larger issue than just what humans have done in the last 40 or 50 years to cause greenhouse increases. For one, there are a number of ways that the Earth actually develops its temperature, and a lot of that has to do with it being a large mass, a lot of weight to the Earth. We're 8,000 miles across, 24,000 miles around, and we have a core that has, maybe from 3 miles to 100 miles of very hard solid material. We have oceans that cover maybe 2/3 of our planet, and the deepest oceans are about 6 miles deep. So we have all of that weight, and it's moving, it goes 24,000 miles around in 24 hours, so that means we're going 1,000 miles an hour. We don't really feel that because of gravity, and we're right on the surface, so we don't sense that we're spinning at 1,000 miles an hour. But not only are we spinning 1,000 miles an hour, but we're going around the sun, and we might be going 20-some thousand miles an hour around our sun, and then our sun is going around in the galaxy at maybe 40 to 50,000 miles, and then our galaxy is going around the universe at maybe 200,000 miles an hour. So there's a lot of speed involved in the universe and on our planet, and that speed creates friction. It creates heat. So part of the heat that we have here on Earth is caused by that motion and friction. Another way that we get heat is that we have a molten core. We have the inside of our planet is made up of a fluid kind of core, and it's very hot. It's probably thousands of degrees warm if you go down a couple thousand feet. I'm sorry, if you go down a matter of miles, you're going to get into some very hot temperatures. If you go down a couple thousand feet, you're going to get warmer temperatures than if you're on the surface. In fact, here in Iowa, if you go down 6 or 8 feet, you can get down to temperatures that stay 50, 54 degrees all year round. So as you go into the Earth, you get warmer and warmer temperatures, and that's because of the molten lava that we have there. Now that molten lava is affected by a number of factors, and one of them is the radiation that comes off of the sun. Now we're lucky that we have an electromagnetic field around our planet that shields us from some of that radioactivity, but there are components of that microwave and energy and X-ray kinds of particles that are coming right on through the Earth. So those particles that come right on through can warm up the molten lava, and at times the sun gives off more radiation than other times, and that would influence the Earth's temperature. It could be that the core of the Earth is warming up because the sun has had an excess amount of the explosions that you might have seen on pictures, where the sun is a huge ball of thermodynamic material, and it's millions of degrees hot up there, and it gives off heat, it gives off this radiation, and those planets that are closer to the sun are warmer because they're closer and because they get more of the radiation. If you go out farther, even to Mars, for example, the temperature is lower there, and Jupiter and Neptune are lower temperatures because of the distance. So they don't get as much radiation, they don't get as much of the radiant heat that's coming off the sun. So we're lucky that astronomers think of us as being in the Goldilocks range, that range from the sun, that the temperatures are in a mild area, basically 54, 55 degrees on average year round. And that's a huge benefit to us because, as far as we know, there are no other planets in our solar system that come close to that. However, there are probably many planets, millions of planets, if not billions of planets out there that could be in a Goldilocks or blue zone where you'd have water and oxygen atmosphere and temperatures that would support life. So when we're looking at variables, those are things that happen, and even on the surface, we can get hit by increased solar winds, increased radiation from the sun. But we also have some peculiarities that our Earth sort of tilts certain ways as it goes around in the orbit, and when it's tilted to the northern hemisphere, tilted towards the sun, that's summer in the northern hemisphere. When it tilts the other direction on the other part of the journey around, then it's the opposite in the southern hemisphere. So we have that tilt, and sometimes that tilt can be a little bit more than another over centuries or thousands of years. That tilt can be just a little bit different, and that can create a tremendous change in the temperature of that region. We also have a variation in the orbit that we have going around the sun. It's not a perfect circle, and sometimes it's elongated a little bit farther, but luckily it comes out 365 days. So as it might be out farther, the temperatures are reduced on the path where it's closer to the sun. They might be warmer. We also have a variation in the galaxy we live in, the Milky Way galaxy. It's now believed to have maybe 100 billion stars, which means there's 100 billion solar systems out there, possibly with planets and everything. They're all on a plane for the most part. In other words, it revolves all around in a plane, and it's not this way. It's this way, but the dimensions through the middle of it can be millions and millions of miles. So it's a big galaxy, and it's an effort to understand how things move inside that galaxy. Our solar system, our sun, and our planets have a tendency to be on a plane that's not exactly perpendicular to everything. So for about 60,000 years, our sun actually comes up above the plane of all of the stars in the galaxy, and then 60,000 years later, it's a little bit below it. So, there, excuse me, there's some huge variations in how our Earth and our sun interact in our galaxy. So there appears to be solar cycles. It appears that every 400 years we have a cool down, every 400 years we have a warm up, and then if you go out, maybe every 10 or 20,000 years we have a warm up and a cool down, and then you go out maybe every 60,000 years we have a variation, and the ice ages, the major ice ages, are about 500,000 years apart. So when you're looking at the Earth, you need to kind of understand that its history is important to how all of these things interact to produce variations in changes of temperatures. So we're a mildly stable planet. We don't feel that the continents are moving, but they are moving. We're a land mass on a molten mass below us, and the planet has a tendency